Good evening, guys. We are now in lesson 7 for chapter 13. This one's called Matter and Energy. This one's a good one, okay? I actually wish, I feel like this lesson, it's like a couple pages long, but I feel like I could spend an hour on this lesson. I won't, but it's a really good one. It's a lot of physics. This is like where we started with E and F. I mentioned before that E and F are a lot heavy with physics, where like A and B were biology, C was like a little bit of geology and astronomy. E started with chemistry, but now we're starting to get into physics, and F is like heavy with physics, but E is like chemistry and physics. But this is a bit of physics here, and I really like this chapter, this lesson. Anyway. So, we're going to start by talking about electrical energy. Electrical energy. Electricity. And so, what are we talking about in the other one? I don't know. Anyway, first we start talking about a battery. Okay, a battery, you can see from the picture, it says a dry cell. Sometimes that's another name for a battery. It says in that little picture with the 1 and the 2, it says in some cases the amount of electrical energy in a circuit may not be great enough to light certain bulbs. For example, a flashlight battery could not light up a 60-watt light bulb from a lamp. Electrical energy can be measured by the size of the bulb it can light. So what they're showing you in that picture is that one battery might not be enough to light up a particular thing, but 2 batteries could. But what you're seeing there is the idea that you can link multiple different batteries and multiple different things on the same circuit. So what we're going to learn about a couple things here. So I want to draw your attention. I should have gone over this first. Let's look at the bottom of page E92. So here in E92, you have a few things here. We have a battery. Okay, we have the battery here. And it's the battery. Sometimes it can be called a cell. It's a power source. Okay. Then we have the positive side, we have the negative side, okay, and it comes down here and gets linked into this light bulb here, and this gets linked as well. Okay, so, and we see inside here, there are these little circles. Okay. This is how this works. Okay. This is the battery source. Okay. This is the battery. This is the power source. All the stuff that happens goes on inside of here. I'm going to make it look like this. This has a little Duracell. Okay. So inside this power source, okay, there's a chemical reaction that takes place. Okay, and what happens is these little things, these little dots are little electrons. You guys remember electrons? What charge does an electron have? Somebody say it out loud. Go ahead. I can't hear you. What charge does an electron have? Very good, Kaylin. Electrons are all negative. Okay, these electrons are all negative. Okay, so these are little negative charges that are flowing around. The reason why it's the electrons is, remember, where are the protons and neutrons? They are located in the nucleus, right? The electrons are on the outside and they are free flowing. So the electrons go here and they're going around. This is called a circuit. It's called a circuit. And basically what happens is the electricity goes around and around and around in this circuit. In order to work, it has to be a closed circuit, not an open circuit. If you were to somehow remove one of these, electricity would not flow. If I were to detach it, either one of these I were to detach, electricity would not work. Okay? In order to get this bulb to light up, you need the electricity you need a closed circuit. That's essentially what a switch does. When you turn a light switch, when you flip it down, what's happening is, if you picture, between the light, there are wires that go between the light to your light switch and then back from your light switch back to the light. Okay, and then the light switch, from the light switch, it goes There are other wires that go to the power source, probably in your basement of your house. And that power source is pumping electricity all the time. And so the electricity goes from the power source up to your light switch, then up to the light, then back from the light to your light switch, and back to the power source in your basement. The circuit breakers, you know, the things that go click, click in the big gray box. Well, what happens when you flip the light switch, when you flip it, when it's off, is a little gap, okay? There's a little gap that happens between the flowing of the electricity. There's a little gap that forms. When you flip the light switch on, it closes that gap and it makes it so that there's a path. If you picture like water flowing down in a hose, and when you turn the light switch off, it kind of like closes up the hose. So there was water coming through, and now it goes whoop, when you turn the light switch off, and now there's a gap, and the water can't flow through, and you're gonna get nothing coming out of the hose. Then when you turn the light switch on, now there's solid flowing there, and it goes through. So that's what a circuit is. The circuit is the path that electricity travels through. Okay, and you need a closed circuit in order for it to work. So what happens here? Okay, let's deal with this first. Electrons are negative. Okay, they are negatively charged. And one thing that you'll hear a lot in physics or chemistry or whatever, when talking about charge, is that opposites attract. Opposites attract. That means that since these are negative, they want to go toward a positive. Okay, negatives want to go to positives, and positive charges want to go to negatives. These negative charges want to go toward positives. Okay, so what happens is they come out of this side. Okay, they come out of the negative, and they go this way, and they go this way, because they want to go away from this negative port, and they want to go toward this positive port. And the easiest way for them to do that is to go through this and to go through the light bulb and get to here. They want to go, here's this negative side, and these electrons right here are like, I want to get away. There's a negative here. He's too much like me. I want to get to the other guy. I want to get to the positive. So he wants to run away from the negative and get to the positive, because this is the easiest way for him to go. And so he goes this way. These little negatives go this way, and through that, they pass through the light bulb, and they carry their energy with them, and they power the light bulb. And they go to this plus right here. Now, you might be thinking, but wait a minute. I thought you said it continually goes in a circle. If they go to this, if they come around and go to this plus, how do they then keep going in a circle? Because inside they come back around and they go this way again, right? They come back around and they go this way again. So you might be like, wait a minute, how does that work? And let me explain it this way. It has to require energy and work to be done. Picture this almost like a ladder. What's it called? The thing you slide. Wow, I couldn't find that word. Picture this like a slide, okay? You have on the slide, naturally what happens on the slide. This slide isn't as good as I was hoping it would be. That's a bad slide. Okay, what happens naturally? Okay, what naturally happens when little Riley, let's draw little Riley, when little Riley goes on the slide, she naturally goes down the slide. Whee! She naturally goes there, right? And if she wants to keep going in a circle, though, she naturally goes down, but what has to happen? She has to exert a force. She has to do work in order to get back up the ladder and go back down again. She's got to kind of do work to keep this going. Same thing happens here. They naturally just flow. As soon as they exit this battery, and there's this negative here and the positive here, they just naturally flow around toward the positive. What has to happen is work has to be done in order to get them to go from here to here, and that work is done inside the battery. There are chemicals inside the battery. It's a chemical reaction, and what happens is that chemical reaction happens and brings those negatives over here. It's almost like it's carrying them, and so that's how there's energy in this battery that gets drained. And a battery doesn't last forever. Every single chemical reaction that happens is more and more life draining out of that battery, because it has to do that work to bring those electrons all the way over, and it can only do that so many times before that battery is dead, dies, okay? And then the battery doesn't have any power anymore. You guys understand? So that's the natural flow. It's almost like this is the ladder. Whee! And then up the ladder. This is a slide. Did I say ladder? This is a slide. Whee! All the way down. And this is the ladder. Whee! Whee! All the way down. Okay? That's what naturally happens. So that is how circuits work. That's a circuit that goes around. And the flow is called the current. How much the flow goes is called the current. This little part that lights up is called a filament in a light bulb. Certain things that you might need to know. Let's see. How the current, you can think of the way that these electrons flow is just like you can think of almost like water. Water has a certain current, a certain way it flows, right? And so if you might be in a little trickling stream, it doesn't have a very fast current, right? The water is coming by like this, right? How much water, you can think of the current as how much water is passing by you every second. If you're in like a raging rapids, they go, how much it's flying by you, there'll be a faster current, how much water is coming by you every second. That is the current, okay? The current is measured in amperes or amps. When you ever hear somebody say like a, 10 amp, blah, 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 what that's talking about is amps are how many of these electrons are coming by every second. The bigger number, the more electrons, the faster flow. And that's the dangerous part. Volt is a measure of potential difference. It's a little bit tricky to understand, but just picture volt is almost like on the ladder, like how high is this ladder? And the higher you go, if you had a little ladder, you're not going to gain very much speed. There's not going to be a lot of energy. There's not going to be a lot of pull on you. Think of what happens when you're at the top of a ladder. Gravity's pulling you, right? And so by the time you get to the bottom, gravity has only been pulling you for a little while. But if you have a really big ladder, gravity's going to be pulling you a lot more, okay? With electricity, it doesn't necessarily mean you're going faster, but it's how much pull. Think about if I drop this marker, okay? I drop it from here. Okay? It's going to have the potential to go that fast, okay? But if I drop it from way up here, it's going to have the potential to go faster. Okay, see how much faster it went? So here, okay, this is how fast it goes, versus way up here, went faster, okay? Because that was a bigger difference that it was able to gain that extra momentum. Same thing happens with voltage. That means like the farther away it is, the more it wants to get there, because these electrons really, really want to get from here to here, and the farther away it is, the more they're going to be like, I really want to get there, right? The farther away they are from that positive. And so an ammeter would measure amps, and a voltmeter would measure volts. Okay, turn the page. There are different forms of energy, page E94 and E95. I'm not going to talk about a ton of things here, but different forms of energy. There's two major forms of energy called kinetic energy and potential energy. Potential energy is like stored energy. You have potential to do something when you're at the top of a slide. I'm going to stick with the slide analogy. When you're at the top of a slide, about to go down, you haven't left yet, you have stored energy based on the pull of gravity. As you're about to let go, then that's how much all of your energy is stored energy, right? Or if you're on a swing and you're right at the back part of your swing, about to swing here, the moment that you stop, you have stored energy that you're about to exert as you go down, but all that energy is stored energy. The other type of energy, the other major type is kinetic energy, and kinetic energy is energy of motion. As soon as you start moving back down, that stored energy is transferred into kinetic energy, and it's stored all the way until you get all the way down. Or on a slide, and when you're at the top, you have stored energy, potential energy, 100% of it, and then you slide all the way to the bottom, and now it's been converted into kinetic energy. During your flight, or during the marker's flight, the marker's going from here to here. At this point in time, it has 100% potential energy, and as it's falling, it's slowly it's slowly transferring 1%, 2%, 3%, 4% into kinetic energy. So by the time it hits the ground, the instant before it hits the ground, it's at 100% kinetic energy and 0% potential. So at the top, it's 100% potential energy, 0% kinetic energy. As it's falling, it's beginning to convert, and then at the very bottom, it's 100% kinetic energy, 0% potential energy. And they equal the same. At the bottom, it's whatever if you say like there's 100, the potential energy is 100 joules at the top. As soon as it's about to hit the ground, you know the kinetic energy is going to be 100 at the ground, right? Kinetic and potential energy. Those are the major forms of energy, but the major types of energy when we're talking about motion, right? But everything we've talked about so far has to do with motion, right? Motion is called mechanical energy. It means energy of motion. There are other forms of energy. We can talk about chemical energy, as seen in the battery. Chemical energy would be seen in the battery. Next one is mechanical. We talked about that. It's a sum of kinetic and potential. It's when you're swinging a swing, that's mechanical energy. When you're going down a slide, it's mechanical energy. When you're riding a bike, it's mechanical energy. The little gerbil in its cage going around and spinning, that's mechanical energy. All of that is, anything that's moving is mechanical energy, right? Next, you have electrical energy. Okay, electrical energy is the movement of electrons. So this part is electrical energy. This part is chemical energy, and here, this part is electrical energy, the movement of electrons. And the last one, next one is thermal energy. Thermal energy is whenever you hear therm, where have you heard the word therm before? The word part therm. Anybody know? Where have you heard therm? Thermometer, right? Thermometer. What does a thermometer do? It measures how hot or cold something is, right? Having to do with heat, right? So thermal is a word part meaning heat. And so thermal energy is heat energy. You know, you go like this, and you can feel there's heat between your hands. What you're doing is you're converting. You can convert between forms of energy. Right then, you are just, what is the movement of your hands? Mechanical energy, right? Motion. And you're using mechanical energy. You're converting mechanical energy into thermal energy. And you can convert back and forth between things. And the last one, by the way, is radiant energy, which is energy of light. And so we have different things that can convert stuff. Like, for instance, you might have solar panels on your roof. I don't know if anybody has solar panels, but if you have solar panels on your roof, what that solar panel is it's basically a converter. Okay, it converts one thing into another. It converts radiant energy, which is light from the sun, converts radiant energy into electrical energy, right? If you've ever seen somebody have like a flashlight with like it has a, I can't think of words tonight, like a handle on it that you spin, that's converts mechanical energy to electrical energy there. You might have something, if you've ever seen like in the movie Aladdin, Iago's like running on that little thing and it's powering the big cloud thing that he has. He's using mechanical energy to convert to electrical energy, right? Anything you move in to get electrical energy is basically we use electricity, but we've tried to find different ways of converting other things into electrical energy. We use batteries, which is converting chemical energy into electrical energy. We use solar panels, which is converting radiant energy into electrical energy. We have other things that can convert thermal energy, heat, into electrical energy. We have turbines, like there's things that spin in the water that convert mechanical energy because of the flow of the current of the water causes something to turn. That converts mechanical energy into electrical energy. Or the wind things, the things that you see that have the big spinny things. I can't think of words tonight. Those things, those spin, which is mechanical energy, and it converts it into electric energy, which can then be used. So those are different forms of energy. This is the last thing I want to cover. Is it? Yeah, that's fine. Let's talk about thermal energy, the different types of thermal energy, because we talked about kinetic and potential, which are the types of mechanical energy, but let's talk about the types of thermal energy. 3 major types. Important to get these differences. This is a big one. We have conduction, convection, radiation. Conduction. In conduction, conduction is where the heat moves, but the matter itself does not move. Like picture you have a cup of coffee, Okay, you have a cup of coffee or a cup. You guys wouldn't drink coffee. Well, you might. Hot chocolate on a cold winter day. You have a cup of hot chocolate and your mom hands it to you and it's in a mug and you go, ooh, that's hot. And you feel the heat and you put the mug down and it smashes on the floor because it was so hot. Oh, it burned me. Okay. Now, did the hot chocolate actually burn you? What happened? No, what happened was the heat from the hot chocolate entered the ceramic mug and the heat from the ceramic mug entered your hand. What happened there was the actual hot chocolate itself didn't ever touch your hand. What it did was the hot chocolate, remember what we've talked about with heat before, heat, energy, goes into the little particles, and the more energy they have, they move around more and more and more and more. They get more and more excited, they move around. And eventually, if you get them excited enough, they break apart and fly all around. That's when something converts to a gas, right? But at the point that it's hot chocolate, they're just very energized. They're moving around, right? And that movement, that heat, that thermal energy that they have, they convert some of it out to the ceramic part of the mug. They're bumping, those particles are bumping into one another and giving the particles of hot chocolate are giving the particles in the mug, the ceramic mug, some of that thermal energy. They're passing it on. They're going, here you go. They're handing it to them. And then the ceramic mug passes one to another, and then eventually they pass it to your hand. So conduction would be like if we're all sitting at a table and somebody at the other end of the table says, can you pass the salt? And you take the salt and you hand it to the person next to you and they hand it to them and they hand it to them and they hand it to them. And it's like it's passed down, that thermal energy is passed down the line, okay? Convection is when the matter itself moves. In that example, it would be like, instead of me just passing it down the line, I get up out of my seat and bring it over to you. Convection is when the matter itself moves. Convection is seen most often with like air. When you have your heat turn on, what happens is those air particles are hot, the warmer air particles, and then it blows directly at you. The warm air particles don't bump one another and pass it on. It actually flows and hits you. The actual warm thing, which is the air particles themselves, actually move across the room and bring heat, that thermal energy with it. So conduction is passing, right? You conduct, you pass it on to one another. Convection is the thing itself moving there. And radiation is heat transferred through electromagnetic waves. We aren't talking about electromagnetic waves yet, but they are electromagnetic rays are things like microwaves and X-rays and even visible light is an electromagnetic ray, and so radiation goes through these electromagnetic rays, and you hear electro in electricity and magnet, and so we'll get into all that in a later chapter. But these waves can heat things up as well, like a microwave. What a microwave does is, interestingly, what it does is all these waves go into the food itself. A microwave isn't like hot like an oven would be. An oven is basically convection. It heats up the air and then blows it at the thing, and it heats up all the air particles inside it, which heats up. It's basically heating up the air. It makes a hot area inside the oven. A microwave doesn't work like that. A microwave sends these electromagnetic rays, and they move the particles back and forth, and then it causes friction because they're moving, they're excited, and they're causing friction, and then it starts to heat from the inside out. These particles themselves, it's heated because they bump one another and they have friction on one another. It's different. If you were to have your hand inside a microwave, it would be very dangerous, but if you feel inside of a microwave, it's not hot. The objects might be hot inside it because they are heated by friction or something like that, but it's not hot like an oven would be hot. That's why if you were to heat something in your microwave and then take the thing out and then put your hand in there, like 30 seconds later, it doesn't really feel hot. Where an oven, you heat something in the oven and then you stick your hand in the oven and it's going to get burnt. But so radiation, actually the interesting thing about radiation as well is radiation doesn't require air particles. Conduction and convection, you need some sort of matter in order to do it. You need air, you need water, you need something you need some sort of particles in order to transfer that thermal energy, and the particle through conduction passes it on, or from convection, the particle itself brings that thermal energy. Radiation, the electromagnetic waves don't need any matter. They can just go. That's why out in space, there's no matter. There's no air, there's no water. It's just, there's empty space. But the sun's rays, which are electromagnetic waves, can get to us because they can travel through anything. All right, that's lesson 7. Sorry, it's a little long on this one, but I find it a very interesting topic, so I tend to talk for a little bit of a long time. See you guys later.